So in the previous session, we have discussed about the quadratic forms. So whenever a second degree homogeneous equation is given to us with n number of variables, usually we take 2 or 3 or at the most 4 variables, then we are going to find a real symmetric matrix from the quadratic form, and we are going to solve it by applying the eigenvalues, eigenvectors, or you can apply the row operations as well as column operations, so that it will be converted into canonical form. So what is the meaning of conversion into canonical form? It is nothing but after doing the specific procedure, it will be reduced into a diagonal matrix. So that after this reduction, the given quadratic form will be expressed as sum of the squares. So this is the whole idea behind it. In the problem solving strategies, I think yesterday we have started a problem, in the middle we have an issue. Now let us begin the same problem again. So do you have any queries with regard to the previous session? Yes or no? Any queries with you? All right. Then I have given some pictures for you as a reference, where the concept of Lagrange's method is given to you. However, it is not that much important with regard to examination point of view, where the given quadratic form will be expressed as sum of the squares by simply doing the arrangement of the terms of the given quadratic form. It is purely applying the concept of a plus b whole square and a plus b whole square by simply rearranging the terms. Have you followed those pictures? Say. So have you seen them? Right? So is that clear for you? How we are applying the Lagrange's method by simply rearranging the terms, or taking the terms as common, doing adding and subtraction of terms. Or do you have any doubts with regard to that? So this is our problem. So we are applying the technique of orthogonal reduction for the given quadratic form, so that it will be converted into canonical form. So the associated matrix with the given quadratic form is 3 minus 1 1 minus 1 5 minus 1 1 minus 1 3. So I think all of you accept with this, and I feel that I have given the corresponding characteristic equation for this matrix, and we have discussed about the eigenvalues, which are nothing but lambda values are given by 2 3 6. Since all the eigenvalues are positive, the given quadratic form, yes, you can write the characteristic equation directly, because you know you have a formula, right? Lambda cube minus trace of the matrix into lambda square, etc. So straight away you can apply that by writing the formula, and you can write that. So you simply mention what is determinant of a minus lambda I, and from that straight away you can write the equation, because you have a formula. So for convenience, you mention the formula here, from that you write the equation. so that the other person will understand what it is actually, how you have deduced that. Now these are the lambda values 2, 3, 6. So we call that it is a positive definite quadratic form. And you know how to solve the eigenvectors, right? So is it necessary for you the solving of eigenvectors here? If you want, let us take one problem here. Or I will write the eigenvectors straight away for lambda is equal to 2, 3, 6. Please tell your feedback. Is that required or not required? Or if you want me to find one value, I will find for one value. Right? Then so the determinant of a minus lambda I, if you consider 3 minus lambda minus 1, 1, minus 1, 5 minus lambda minus 1, 1 minus 1, 3 minus lambda. So if you have substituted lambda is equal to 2, then the corresponding equivalent matrix will be 1, minus 1, 1, minus 1, 3, minus 1, and 1, minus 1, 1. Now we are going to apply the operations as R2 tends to R2 plus R1 and R3 tends to R3 minus R1. So this will be equivalent to 1 minus 1, 1 on adding 0, 2, 0, then you have 0, 0 and 0. So from this, the rank of the matrix is 2 and you are going to determine the values. So here you are going to take among the three variables one variable as constant. So how we are going to take the constant here? Any guesses? Say. Suppose if we have taken that z is equal to k, a constant. So from the second equation, you have 2y plus 0z equal to 0 implies that y is equal to 0. Again, from the first equation, you have x minus y plus z equal to 0. This implies that x, since y is 0 and z is constant, so this is equal to x is equal to minus k. So what is the corresponding vector? X, y, z is equal to minus k, 0, k, nothing but k into minus 1, 0, 1. This is the corresponding vector. Okay. So in the similar manner, for lambda is equal to 3 and lambda is equal to 6 also, we will find the respective vector. So if you have found them, the values happen to be minus 1, minus 1, minus 1 is one vector. I am not writing the constant there. So whenever I say about the eigenvector, we don't consider k, we simply consider this vector, minus 1, 0, 1. And the other vector happen to be 1, minus 2, 1. However, you can neglect minus 1 also, you can take it as 1, 1, 1 also. That is also taken into consideration for this. Because if you have taken k is equal to minus 1, the corresponding vector is nothing but 1, 1, 1. That is also taken into consideration. So these are the three eigenvectors corresponding to the distinct three eigenvalues 2, 3, 6. So if you want me to solve for one more value for lambda is equal to 3, I will solve it for lambda is equal to 3 also. Otherwise, please take a note of those vectors, then I will move ahead. Yeah. So So in this problem, orthogonal reduction is nothing but you are going to find an orthogonal matrix P. Usually we will get a diagonal matrix. How we are going to get? P inverse AP equals to D. Since P is a orthogonal matrix, P transpose is nothing but P inverse. So our resultant matrix is nothing but P transpose AP equals to D. So we are having the relation as P transpose AP equals to D. This is our relation. Okay. Now, how to find phi? Since you are having a orthogonal matrix, we are going to normalize the above vectors. What is meant by normalization? We are simply taking the unit vectors in the matrix P. So you are going to write a 3 by 3 matrix P where the columns are nothing but the unit vectors, you can say, are mutually perpendicular vectors. If you observe that the eigenvectors what you have obtained, they must be pairwise orthogonal. So what does it mean? If you consider any two of them, if you have calculated the dot product, it must be equal to 0. So you can check that. So if you consider the product of these two, 1 into 1, 1 into minus 2, 1 into 1, it is 0. If you consider the product of these two, it will be 0. Again, if you consider the product of these two, it will be 0. Did you observe? So they are pairwise orthogonal. So whenever you have a vector, in order to get unit vector, we should divide with its length, the magnitude. So for the first vector, the corresponding normalized vector is nothing but square root of minus 1 whole square plus 0 square plus 1 square. You are going to divide with this value. So the corresponding vector is nothing but minus 1 by root 2, 0 and 1 by root 2. Similarly for this, the magnitude is root 3. Dividing with root 3, it will be 1 by root 3, 1 by root 3 and 1 by root 3. Here, what will be the magnitude? Can you say? Root 6. So if we divide with this, it will be 1 by root 6 minus 2 by root 6, 1 by root 6. This is our matrix P. Okay. Is it clear for you or any questions to you? Any one of you? Now, if you multiply the three values, P transpose, the given matrix A and P, you are going to get the diagonal matrix which is nothing but 2 0 0 0 3 0 0 0 6. That was the matrix. Okay. So what is the overall procedure? From the given quadratic form, we will take the associated real symmetric matrix, find the eigenvalues and eigenvectors. Usually eigenvectors are pairwise orthogonal because we have taken distinct eigenvalues. Now normalizing the eigenvectors, nothing but dividing with their magnitude, you will get the respective unit vectors. You consider them as columns of the matrix P. So P transpose AP is nothing but required diagonal matrix 2 3 6. Okay. Is it clear or any doubts? Right. Now From this, if you want to find what is the rank, what is index, what is signature, etc., etc., since you have calculated all the three values which are non-zero eigenvalues, rank of the matrix is nothing but 3. And what is index? How many positive values are there? 3 positive values are there. So index is 3. And what is signature? 2s minus r. I have given the formula. So 2 into index minus rank. So nothing but 2 into 3 minus 3, nothing but 3. That is signature. If you want to write the values of index, rank, signature, etc. You can take one more definition for signature as the difference between number of positive values minus number of negative values. So here the eigenvalues are 3 positive values which are, there is no negative value. So signature is nothing but 3 minus 0, which is 3. That also you can write. There are two definitions for the signature, positive values minus negative values. Okay. If this problem is clear, I want to take one more problem on this model where eigenvalues are repeated. I want to discuss that case. Can I take that? Okay. Now, this is our problem 6 minus 2, 2, minus 2, 3, minus 1, and 2 minus 1, 3. Here, I am not writing the quadratic form. I am straight away considering the matrix. Is that okay for you? Right. So, this problem we have solved already for the calculation of eigenvalues as eigenvectors. However, if we have considered one more time, the characteristic equation is nothing but lambda minus 2 whole square into lambda minus 8 equal to 0. So the lambda values are lambda equals to 228. Now you know how to calculate the corresponding eigenvectors. So if you have considered them, it will come as the values 2 minus 1, 1, that is one vector, 1, 2, 0, that is one vector, other vector is 0, 1, 1. So where this vector happened for lambda is equal to 8 and these two vectors are happened for lambda is equal to 2. So is that required for you, the calculation of eigenvectors one more time? No need. Right. So here, if you observe that, are they pairwise orthogonal? If you consider the dot product of any two, is it giving 0 to us? Yes or no? So you can observe one interesting thing that these two are orthogonal. Accepted? Right. These two are orthogonal. But these two are not orthogonal. So here I am defining or I am finding a new vector which is orthogonal to these two. So that I will consider this vector, this and the new vector. Right, or I will consider this one and the new vector. So that I will get three distinct pairwise orthogonal vectors, and using them I will consider the orthogonal reduction. So how I am finding them? Since these two are not orthogonal, you simply consider these two values and find a combination. So you are finding a vector which is perpendicular to these two. Try to understand that. So if we have written that alpha into 1 to 0 plus some delta into 0 1 1. So I am going to find a vector which is perpendicular to these two, means if we have find any combination where alpha and delta are nothing but some numbers, we call it as a linear combination. So these two vectors together constitute a line. So you are finding a vector which is perpendicular to that line. That is the whole idea behind this, right? So how to find these values? So from this you can say that it is nothing but alpha, 2 alpha plus delta, delta. So I am going to find a vector which is perpendicular to this, right? So please understand that this vector is going to be perpendicular to above two vectors. So this is perpendicular to this and this is perpendicular to this, right? So how to determine the values of alpha and delta here? So if you observe that, you can say this vector is perpendicular to 0 1 1, hence the dot product must be equal to 0. So you can say that alpha dot 0 plus 2 alpha plus delta plus delta into 1 equal to 0. This implies 2 alpha plus 2 delta equal to 0, implies alpha is equal to minus delta. So if you take alpha is equal to 1, then substituting the respective values there, the vector is going to be 1 1 minus 1. Is it clear? Right. Now, what are the vectors we are considering so that they are pairwise orthogonal? This is my invented vector. This is the vector corresponding to lambda is equal to 8. I should take definitely. Among these two, I should pick one. So I am taking the vector 0 1 1. So what are the three vectors? 2 minus 1 1, 0 1 1 and 1 1 minus 1. If you write them together, they are pairwise orthogonal. You can check that. So why I am writing a combination? The combination gives a new vector which is perpendicular to both the vectors 1 to 0 as well as 0 1 1. So assuming that vector alpha 2 alpha plus delta delta is perpendicular to 0 1 1, solving the respective dot product equal to 0, I will get alpha is equal to minus delta. So randomly take alpha is equal to 1. So this is the corresponding vector. Or alpha is equal to minus 1, you can take that vector also, no problem. So these two vectors I have taken. Now for orthogonal reduction, after finding pairwise orthogonal vectors, I need to normalize them. Because in the orthogonal reduction, we consider the normalized vectors. So what is the length here? It is the length root 3. So one vector is 1 by root 3, 1 by root 3 minus 1 by root 3. Again, I am considering this. What is the length here? 6 is the length. So 2 by root 6 minus 1 by root 6, 1 by root 6. Here the length is 2. So 0, 1 by root 2, 1 by root 2. So this is my model matrix P. And if you consider P transpose AP, which will give our diagonal matrix nothing but 2 0 0, 0 2 0, 0 0 8, depending upon the vectors order you have written, or 8 0 0, 0 2 0, 0 0 2. You are taking a vector which is perpendicular to 1, because 1 to 0 is not perpendicular to 0 1 1, right? So I am finding a vector which is perpendicular to one of them. So I am replacing 1 to 0 with a new vector. I am finding a new vector in place of 1, 2, 0. So I don't consider 1, 2, 0. I consider only 0, 1, 1. Because I need pairwise orthogonal things. However, these two are orthogonal. There is no need to cross check. So if we have found a vector which is perpendicular to this, that is sufficient. Okay? Any other cross questions from anyone? Or is the approach clear to all? So I have discussed the two things. One, if the eigenvalues are distinct, obviously the eigenvectors are pairwise orthogonal. So you can normalize them. You can go for the orthogonal reduction. Whenever the eigenvalues are repeated, the eigenvectors need not be pairwise orthogonal. In such case, among the two, you are taking one vector and replacing with a new vector by using this type of procedure. And doing normalization, finding the P transpose AP is as usual. No difference at all. So these are the two things about orthogonal reduction. Then I am going to take the other method, reducing the canonical form by using row as well as column operations. Okay? Shall I proceed? Right. Just wait for a moment, I will take the part. So this is my quadratic form. So if you have written the associated matrix with it, it will be 10 minus 2 minus 5. Then the second row happened to be minus 2, 2, 3. And the third row happened to be minus 5, 3, 5. This is our matrix A, which is associated with the quadratic form. Is it okay? Now, the interesting thing here is you are going to write this matrix as I3, A, I3. So, this is the 3 by 3 matrix. I have considered two 3 by 3 identity matrices. So, on this A, I am applying row operations as well as column operations, and I will reduce this into the form diagonal matrix form. Since I am applying the both operations row and column, this is the prefactor and this is the post factor. I will apply row operations only on the prefactor. I will apply column operations only on the post factor. The interesting thing here is, since we need to get the form as P transpose AP, so we are taking into consideration that whatever the row operation you take, that corresponding column operation, the conjugate column operation, we consider. So while doing the problem, you will understand. So this is nothing but 1 0 0 0 1 0 0 0 1, A 1 0 0 0 1 0 0 0 1. So the operation what I am going to apply here is R2 tends to 5 R2 plus R1, R3 tends to 2 R3 plus R1. And for applying the column operation, I will apply the operation as C2 tends to 5 C2 plus C1, C3 tends to 2 C3 plus C1. Did you observe the pattern? Whatever the row operation is applied, the same column operation is applied here. Did you observe? That's what I am mentioning here. So whatever the operation you have written, the same column operation you are going to apply here. Clear or not clear? Because it is a real symmetric matrix, the same thing you are going to apply here. Accepted? Any doubts? Fine. So I am doing that respective transformation. So I think it will come as tan 0 0 0 40 20. So again, I will apply the operations as R3 tends to 2 R3 minus R2, and C3 tends to 2 C3 minus C2. However, you can cross check or cross verify for the operations. So this is my final output. So please concentrate on the procedure, what it is described. So applying the operations is at your will. The only thing is, whatever the row operations you are applying, the same corresponding column operations you are applying here. So you have the format as D is equal to P transpose AP. You can check for that. Okay. So from this, you will get the matrix as P is equal to 1 1 1, 0 5 minus 5, and 0 0 4. In other words, you are going to have a lower triangular matrix as well as upper triangular matrix. However, if the transformation is asked for you, then the formula is x is equal to p into y. So x is equal to py, this is equal to p into y1, y2, y3. So x, y, z is equals to multiplying this y1 plus y2 plus y3, 5y2 minus 5y3, 4y3. So this is x, this is y, and this is z. Those are the respective values. And what will be the given quadratic form? Every quadratic form can be represented as x transpose ax, which is equivalent to y transpose dy. So y transpose is nothing but y1, y2, y3. D is our diagonal matrix. So on multiplying this, 10 y1 square plus 40 y2 square is the respective transformation. Okay. However, the corresponding linear transformation in general will not be asked, but if you are interested, you can take a note of this. Fine. Now, from this, you can observe that from the diagonal matrix, what are the eigenvalues are there? 10, 40, and 0. Since 0 is presented as an eigenvalue, the given quadratic form is positive semi-definite. Since two eigenvalues are there which are positive, 10 and 40, its index is nothing but 2. So what is the signature? Number of positive values minus number of negative values. Since no negative eigenvalue is there, so 2 minus 0, which is 2, is the signature for the given quadratic form. Clear? So this is the overall idea. So if you are interested, I will take one more problem which gives a good idea to you. Is the procedure clear for all? Any questions, please? So there are in total 3 methodologies are there. One, Lagrange's reduction, which is of less use generally in practice. Second, orthogonal reduction, we have discussed earlier. And now this is the canonical form. This is the regular method, applying row operations as well as column operations. Row operations will be applied on the prefactor, column operations applied will be on the postfactor. So the respective new transformation will be found using this. And from the diagonal matrix, we will write the new transformation. Okay. If everyone is clear, I want to take a new one. Shall I continue? Transformation is nothing but 10 y1 square plus 40 y2 square. Please understand, the given quadratic form is nothing but x transpose ax. In the last class we have discussed it, isn't it? This is our given quadratic form. This quadratic form, after the reduction, will be converted like this, y transpose dy, which is nothing but sum of the squares. How the sum of the squares are taken? This is y transpose, diagonal matrix D and y. So multiplying that, 10 y1 square plus 40 y2 square. Lash row and column operations. Okay, you forget about that, but this is the procedure usually we do. Okay. So if you apply this operation, the lash row will be 0 as it is. There will be no change at all, isn't it? And this is the modification there, I hope. So you remember that procedure. You can try with your own operations. There is no need to follow the same kind of operations what I have mentioned here. But the typical procedure is this. The typical procedure is this. Applying row and column operations by this type of method. Right. I want to mention one more thing, that by taking one more example on the same pattern, and I will give one more shortcut also over this type of procedure. What we do in the examination point of view for speedy calculation. So just hold on for a moment. Suppose this is my matrix. So writing this matrix in the form of I3, A, I3, I will apply the row operations as well as column operations. I am applying like this. So R2 tends to R2 plus R1, R3 tends to R3 minus 2R1. Also C2 tends to C2 plus C1, and C3 tends to C3 minus 2C1. You will get the thing as 1, 0, 0, 0, 0, 4, 0, 4 minus 2, A. Just hold on a moment, I will take like this. 1, 0, 0, 0, 0, 4, 0, 4 minus 2 is equals to 1, 0, 0, 1, 0 minus 2, 0, 1, A, 1, 1 minus 2, 0, 1, 0, 0, 0, 1. So let us assume that the given operations as well as the resultant values are correct. So then you are going to do that. So this is my result. Now I can further modify this, the quadratic form. How I can do it? So at this place of 8, I can make it as 1, and also this 2 can be made as 1. Since we are applying row operations as well as column operation together, in order to make this place as 1, I will apply the operation as R2 tends to 1 by root 8 R2 and C2 tends to 1 by root 8 C2, so that this will become 1. Similarly, in order to get 1 here, so I will say that R3 tends to 1 by root 2 R3 and C3 tends to 1 by root 2 C3. So this is one way of applying the operations, right? So the result will be given as 1 0 0 0 1 0 0 0 minus 1 is equals to 1 0 0 minus 3 by root 8, 1 by root 8, 2 by root 8, minus 2 by root 2, 0, 1 by root 2. A, and similarly you will get the respective values here. So one interesting observation here is, for making the diagonal entries simplification, we will do by dividing with irrational numbers also. Dividing with root 2, root 5, root 6 also we will do. In order to make the place of 8 as 1, we will apply the operations in this manner. That's why I have taken this into example. Now, if you observe the diagonal entries 1, 1, minus 1, so what is the index? There are only two positive values, 1 and 1. So the index is 2. What is the signature? Number of positive values minus number of negative values. So it will be 2 minus 1. 1 is the signature. Okay. So in this way, we will find the corresponding canonical form. So some authors, the one thing is, reducing the diagonal form is nothing but having the eigenvalues on the diagonal, isn't it? Yes or no? Because you are applying the same operations, right? Every time, if you apply R2 tends to R2 plus 2 R3, the corresponding column operation should be applied. Please understand. I want to make that value as 1, that's why I have taken like this. For example, let us assume that for the given matrix, the eigenvalues are nothing but 1, 1, minus 1. Since I don't know what are the eigenvalues, but on the diagonal, eigenvalues will come always. So in order to get the eigenvalue on the diagonal, I should apply the operation like this only. So one useful thing is, in order to get a clarification over these operations, once you found the matrix, please determine the eigenvalues first. What are they? So up to half of the problem, it is clear for you how to apply the operations. While applying the row operations with regard to this root part, then based on the eigenvalues, you can go for that. On what number you are going to divide. Root 8 or simply 8. That will give the clarity. Okay. Is that clear? Right. Now, every time writing the given matrix to identity matrix, applying row and column operations as well is a difficult task. It takes nearly very good time. So even though you have done a speedy calculation, it takes much more time for us. So in order to avoid that, one procedure is described, which is nothing but writing the augmented matrix. So we apply row and column operations both on left side, but on the right side we apply only row operations, we skip column operations. Why you are skipping the column operations? Because if you have done D is equal to P transpose AP, the transpose of the matrix will appear here. So in order to take two operations at once, you stick on to one operation, you skip the other portion of operations, take the transpose of one matrix which gives the other. So that is the technique of augmented matrix. I want to take one problem on this, which give a knowledge how to do in the exam point of view. So this is the matrix 1, 2, minus 3, 2, 5, minus 4, minus 3, minus 4, 8. This is my matrix. Now what happens? I consider the augmented matrix A by I. So this is my matrix A as well. So nothing but 1, 2, minus 3, 2, 5, minus 4, minus 3, minus 4, 8, oblique, 1, 0, 0, 0, 1, 0, 0, 0, 1. Now what happens on this portion, I will apply row operations and column operations as well and reduce this part into diagonal model. But here I consider the same row operations applied on this left side part. I will avoid the column operations application on this part. Is it clear? Right. Now let us do the part. So I am going to do the operations as R2 tends to R2 minus 2 R1. So R3 tends to R3 plus 3 R1. Similar column operations. C2 tends to C2 minus 2 C1. C3 tends to C3 plus 3 C1. Right? You are going to get the corresponding thing as 1 0 0 0 1 0 0 0 minus 5 oblique 1 0 0 minus 2 1 0 3 0 1. I think you need to just go for a modification here. Just give me a moment, I will say. So once we have applied the 4 operations, it will be transformed into this model. Then again apply these operations, then it will be converted into this model, which is a diagonal matrix, which is somewhat different. So please take a note of it and assume that the operations are correct and the values are correct. So don't cross check it. Just concentrate on the procedure, what it is actually. The only thing is, on the left side part of the augmented matrix, we apply same row and column operations, the conjugate model as it is. But on the right side identity matrix part, we consider only row operations, we skip column operations. So whatever the row operations are there, we simply apply these 3 row operations on this part only. We avoid applying the column operations. Okay? Is that clear? Right. So this part is nothing but P transpose. So in order to write P, you consider transpose of this matrix. Nothing but 1 0 0 minus 2 1 0 7 minus 2 1. This is our matrix P and this is nothing but P transpose. And this is the diagonal matrix D where 1 1 minus 5 are nothing but the eigenvalues. Okay? So the simplest approach is this one, writing the augmented matrix, applying row and column operations, and from this part writing P by taking the transpose of this part. So you can say that P is the upper triangular matrix and P transpose is the lower triangular matrix. We will get D as well. Okay? So this is somewhat a comfortable approach while solving the problem. So far we have discussed with the canonical form where the entries are real numbers. I just want to take one problem where the entries are complex numbers. This kind of problem occasionally you will get entries are complex numbers, but however If you have done with one problem, you will get the whole idea what it is actually. So this is the problem. So I have taken a Hermitian matrix given by 1, 1 plus I, 2I, 1 minus I, 4, 2 minus 3I, minus 2I, 2 plus 3I, 7. This is my Hermitian matrix H. Now, from this, I am writing the augmented matrix as 1, 1 plus I, 2I, 1 minus I, 4, 2 minus 3I, minus 2I, 2 plus 3I, 7, oblique. So here also for the complex entries, I will apply row operations as well as column operations on this model and reduce this into diagonal form, and only row operations are considered on this portion. Okay, and we are applying a corresponding conjugate column operations. So once I have written, you will get the idea. So R2 tends to R2 you can say R2 minus this R1. Now you can observe in applying the operations that here in order to get 0, you should multiply here with minus 1 plus I. Accepted? Yes or no? So in order to make 0 here, you need to take the conjugate here. So what is the conjugate of 1 plus I? Nothing but 1 minus I. In other words, for this operation value, you are taking the conjugate. So for plus I, the conjugate is minus I. So I am doing with minus this one. So there is a difference in the operations whenever complex entries are there. So since to get 0 here, we should multiply with plus 2I. In order to get 0 here, you should multiply with minus 2I. So did you have the difference? Observe the difference here. So whenever you are multiplying with A plus IB for row, for column, you take the corresponding conjugate A minus IB and you perform the same operation. So row and column both will be performed on this model, but only row will be performed on this model, right? Then it will come as, I will write the part. So applying both row and column, it will be transformed into this model. Applying only row, it will come into this model. Again, you apply the operation as R3 tends to 2R3 minus 5I R2, and column operation C3 tends to, right, 2C3 plus 5I C2. Then we get the matrix as 1 0 0 0 2 0 0 0 minus 38 oblique 1 0 0 minus 1 plus I 1 0 5 plus 9I minus 5I 2. And the given matrix is converted into diagonal form. So for complex matrices, the diagonal form is defined as D is equal to P transpose HP bar. So since this is P transpose, for having P, take a transpose of this matrix. So it is going to come as P is equal to 1 0 0 minus 1 plus I 1 0 5 plus 9I minus 5I 2. So if you multiply P transpose H and P bar, for this you are taking the conjugates, then you will get this diagonal matrix 1 0 0 0 2 0 0 0 minus 3 8. And from this you can specify the rank signature as well. There is no change in the definition. The only difference is here you are applying the complex operations by taking the respective conjugate for the row operation. That's it. So you please take a note of this. I think it is one of the previous year questions. You can check for that. So this is the whole discussion about the quadratic forms. The three methods based on the reduction into canonical form or normal form you call. So unless orthogonal reduction is asked, we don't apply the eigenvalues, eigenvectors technique. We always stick on to the row operations technique. Okay. However, if you are interested, you can apply that, but always we apply row and column operations technique only for the reduction into canonical form whenever a quadratic form is given to you. Okay. We write the two identity matrices I3A, I3. We apply the respective operations and convert that into a diagonal form. Is that clear, or do you have any other doubts? So I try to give an assignment comprising this entire quadratic forms, system of equations, eigenvalues, eigenvectors, etc., etc. And before that, I just want to give a small discussion over some previous year questions over this matrices concept. Okay. If you have noted this, please inform. I will go with that part. Any other queries with this method described? The augmented matrix model, or is that comfortable? Say. All right. So this is one of our problems. There is a matrix given A is equal to 2 minus 2 2 1 1 1 1 3 minus 1. He has mentioned that find eigenvalues of B cube where B is equal to C inverse AC and C is a non-singular matrix. So if you have seen some of the previous year questions, this is one of those questions. So I have given a matrix A. I need to get the values, the eigenvalues of B cube where B is equal to C inverse AC and C is a non-singular matrix. So any idea for anybody over this? Exactly. Here C is equal to P. So whenever you have a phenomena like this, what you can say about these two? Don't misunderstand that B is a diagonal matrix here. Don't feel that. Okay? Whenever you have relation like that, what we can say about A and B? We call them as similar matrices. Agreed? I have given the definition that a matrix is similar to another matrix whenever you can find a non-singular matrix that P inverse AP is equal to the matrix. And as I have given some postages about eigenvalues properties, it is given that similar matrices will have same characteristic polynomial. So whatever the polynomial of B, which is also applicable for A, in other words, A and B will have same characteristic polynomial. So if you know the eigenvalues of A, the same eigenvalues are applicable for B also. Agreed? Are you getting the concept? Because both are similar matrices. Whenever matrices are similar, they have the same characteristic equation or characteristic polynomial. Hence, they will have the same eigenvalues. So, since we need to calculate eigenvalues of B cube, whenever you know the eigenvalues of B, if you cube them, those are nothing but eigenvalues of B cube. So let me say, if eigenvalues of A are nothing but 1, 2, 2, let us say, then what are the eigenvalues of B cube? 1 cube 1, 2 cube 8, 2 cube 8. These are the eigenvalues of B cube. Okay? So please take a note of that. Is the approach clear to all? Right. So if you have noted, I will take the other one. B may be a diagonal matrix, may not be. That doesn't matter. That doesn't matter. If B is a diagonal matrix, we can say that A is diagonalizable. So we are not discussing about diagonalizability. You are talking about the similarity. These two are similar matrices, so they will have the same characteristic equation and characteristic values. That's all. It is not mentioned that B is a diagonal matrix. If B is a diagonal matrix, automatically the eigenvalues of A are nothing but the diagonal entries of B. So automatically you will get the same diagonal values. There is no need to find separately. The question is very clear there. So irrespective of nature of B, whether it is a diagonal or not, if you want to find eigenvalues of B, B cube, they are nothing but cubic values of eigenvalues of A, because they are similar matrices. One more problem is, I have given a matrix 26 minus 2, 2, 2, 21, 4, 44, 2, 28. Suppose this is the matrix A, let me say. So it is given that, prove that square root of lambda 1 square plus lambda 2 square plus lambda 3 square is less than or equal to square root of 1949, where lambda 1, lambda 2, lambda 3 are nothing but eigenvalues of A. So you know how to calculate eigenvalues of A. You have a formula to write that characteristic equation. From that you can decompose that. I can say that the eigenvalues of A are happen to be 26, 21 and 28. Lambda 1, lambda 2, lambda 3 values. So that if you have squared them, I can say you will get lambda 1 square equal to 676, 441 and 784. So if you observe that the sum will be equivalent to 1901. I hope so. So it is always less than or equal to 1949. This is one solution. So the only difficult thing here is calculation of the eigenvalues. You will get a big numbers like 26, 21, 28 for the factorization, which is somewhat difficult in computation. That's all. I think for the rest of the problems, you are comfortable in the exam point of view for the previous year questions. If you have doubt on solving them, we will have a discussion later on the doubtful questions. So at this moment, I want to conclude my discussion over matrices of linear algebra part. So from tomorrow onwards, I want to start with the vector spaces concept. I think which is totally different for you, and a good weightage of questions will come from this portion. So the only difficulty is earlier you need to get tuned with 10 to 20 definitions. Once you know them, then it is nothing but solving problems. The advantage of vector spaces is here in matrices the solution is big, but here in vector spaces the solution is very small. I can say if you have taken 1.5 pages to solve a problem here you will take 3/4 of a page to solve a problem with same weightage. And occasionally you will have the repetition of questions from this portion. You cannot expect the repetition of questions from matrices part, but you can have an expectation of repetition of questions from vector spaces part. So these are compared to matrices, these are very good for the calculation purpose and easy to understand. Once you know the common definitions, around 10 to 20 definitions are there. You can call them as definitions or formulae, whatever it is. Then it will be very comfortable for you problem solving on vector spaces, right? So at this moment I want to conclude my discussion here. Thanks for your cooperation. Tomorrow we will meet with the new concept. So what are the doubts you have, you please tell and we will discuss later. If anybody has any other doubts. If you want to add something, you can add. Any questions, please, to anyone? Then you can search for a shortcut, but I won't rely on the shortcuts always. You can search for this Quora.com, etc.